Guess what? It's almost time for final exams. Seniors, your exams are going to be the coming up week on Tuesday and Wednesday. Please make sure that you know when your exam is going to take place. If you are in hour 3, 4, or 9, yours is on Tuesday. During class, you'll report to the library. If you are in hours 2 or 6, 7, yours is on Wednesday. You will report to the library. The exam has 3 parts. First part, concepts part, multiple choice, 35 questions taken on a Scantron. Second part, short problems. We'll look at some short problem examples in this review. And the third part is an essay. The essay is actually here on your review. It's an open-ended question, meaning there's no right or wrong answers, only more or less depth of thought and reflection shown. So please make sure to take the question very seriously. The question is asking you to discuss 2 skills you feel you've strengthened as a result of your effort in science class, and to explain how these skills will serve you in the future. Skills are things you can do. Please do not talk about what we did. Talk about what you can do. What do you know how to do better now than you were able to do before? Or what areas do you think that you've improved? Your exam will have all the needed tables and everything else that you'll need. I'll even provide you with a calculator because you're going to need one of those as well. You may not use any of your study materials on the exam because it is a final exam, not a regular assessment. So please come prepared. So I'm going to go through a few things with you that are from the exam. Not everything in the review packet, just some problem-solving aspects. The one section is going to be about temperature, heat, measuring energy by calorimetry. You can look back at some of my previous video demonstrations. You can also use your textbook as a reference. The concepts that are going to be covered, I'm not asking you to memorize, but you should know how to use or recognize them when they're being used. So, there is one practice problem here, a problem similar to one that I'll ask you to calculate. This one is asking you to use calorimetry to solve a problem about the mass of a tub. So the tubs are very heavy. You might not be able to lift it up and put on a scale, but you can use calorimetry to figure out how much it weighs. Look carefully at the question to see what you're given. Remember that we're using the heat equation. The heat equation has terms heat equals the specific heat capacity of a material times its mass times its temperature change. Specific heat capacity describes how much energy it takes to change something's temperature for each gram and for each degree of temperature change. Mass is how much material something has. And the temperature change is found by taking the difference between starting and ending temperatures. Difference means subtract. So in the problem it says you fill the tub with a lot of water. It's about 45 gallons of water, but that's its mass, 170,000 grams. And the water cools down in the tub because it's just sitting out, and that's what happens to your water in the tub. It cools down from 48 down to 37 degrees. And the tub warms up because it was a cold hunk of metal before. Temperature goes from 19 degrees up to 37. The specific heat capacities of the iron in the tub and the water in the tub are given. And so the first thing you should be able to do is find the values that you need in the information that you're given. So, the mass of the water in the tub. Well, it says right here, that's the mass of the water in the tub, 170,000 grams. The starting temperature of the water in the tub started at 48 degrees Celsius and it cooled down to 37 degrees Celsius. So how much did its temperature change? The temperature goes down by how much you get when you subtract 11 degrees Celsius. We do not know the mass of the iron in the tub. That's what we're trying to find. But we do know its starting temperature. The starting temperature was at 19 degrees and then it warmed up to 37 degrees. The temperature went up. And the temperature change when it went up, you find by subtraction, and it was 18 degrees. 37 minus 19. So one thing is cooling down, the other thing is warming up because heat is being exchanged between them. The amount of heat that's lost by the water as it cools down is the same as the amount of heat that the tub gains as it warms up because it's the same energy. It just moves from one thing to another. How much the temperature changes depends on the specific heat capacity of the materials because some things change temperature more easily than others. It takes more energy to change the temperature of water, each degree for each gram, than it does for metal, for the iron. So now when I go to do the calculation part, I'll find the values that I need right here. So the first step, how much heat was lost by the water in the tub? So I need to know first what was the specific heat capacity of the water in the tub. All of my values are about water. So I'm going to make sure that I use only numbers that are about water. Here I color-coded them blue. Specific heat of water, 4.184 joules per gram degrees Celsius. How much energy it takes for each gram to change each degree Celsius. Times the mass, 170,000 grams, times the temperature change, which was 11 degrees Celsius. Multiply those together. Now when I do this, I'll show you the calculated answer and I'll show you the specific, significant figures answer. 7824080 is what you get on the calculator. And if you are comfortable with the significant figures, by all means show two significant figures if you know how to do that. If not, make sure that you get the calculated answer correct. It is two significant figures because this value has two significant figures, and so does this one. And we round our answer to the fewest significant figures when we multiply or divide. So that's how many joules of heat energy were lost by the water. Where did it go? It went into the iron. So in the next step, when you do the calculation and you need to know a heat value, it's the same heat that the water lost, because there's only one heat, the heat that goes from the warm thing to the cold thing. So I'll use that heat in my next step of the calculation. Joules on top. The specific heat capacity of the iron given in the problem, 0.449 joules per gram degree Celsius, and the temperature change was 18 degrees. Remember to use your order of operations. So the top number divided by these two numbers multiplied by each other. So the significant figures answer to that would be, well, not yet. It's 8.082, but now I'll divide and round to significant figures. The top number divided by the bottom number is 965,107.6, on and on and on. But if I rounded that to two significant figures, 2 because they're 2 or 2, if I rounded it to two significant figures, I get 970,000 grams. That's a pretty heavy tub. 970,000 grams. It should be heavy, it's a big tub. If you are not sure about the rounding part, get it calculated. Give me the calculated answer. That will show me that you knew what you were doing. If you can round to significant figures, that shows me a greater level of understanding. But still, make sure that you get it calculated correctly. There's one extra step here in the problem that I actually made a mistake on. This is a conversion between grams and pounds. It should be 0.0022 pounds per gram. So if this is how many grams, is how much the tub weighs, 970,000 grams, and I multiplied it by how many grams there are in a pound, or how many pounds are in a gram, I would get 2,100 pounds. That's a pretty heavy tub. That's more than a ton. So when you're doing a problem like this, the main thing is to make sure that first you can find the information that you need from what you're given, that you know to subtract to find a change, that you can put the values where they belong, making sure to use values that you're asked for. If your calculation is about water or about the other material, make sure that you use the values for those materials. Use your correct order of operations. There will also be questions about atomic structure, periodic trends, chemical bonding, chemical formulas. Again, there are sections in your text that can be helpful for background information. You can also use anything from the video demonstrations. You should be able to identify what are the parts of an electron configuration and what they represent. There's a similar question on one of your recent assessments. Why are elements arranged the way they are in the periodic table? And what do they have in common? They're electron configurations. We looked at that by making the models and putting them on the ceiling. And then what affects the positive and negative charge attraction between the nucleus and in particular the valence electrons? How does the size of the positive charge in the nucleus, the distance to the outer electron orbitals, and the effect of shielding by the inner orbitals affect that attraction between the positive and negative charges? There are a number of things you should be able to do. If I give you an element and the orbital filling diagram, you should be able to do several steps with that information. I'll practice a couple with you. Okay, looking at the periodic table, remember that there are two sides to the periodic table. The sides are divided by a stair-stepping line. On the left side are elements that we call metals. Metals react by losing electrons. And on the right side we have elements that are nonmetals, elements that react by gaining electrons. And the elements that are touching the line, the ones that, except for aluminum, those are metalloids. Those react either by gaining or by losing electrons, depending on who they're reacting with. So we'll use information from the periodic table to work on some examples from here, what you should be able to do. So, a couple templates here. I'm going to do magnesium and chlorine. First, you should be able to find those elements on the periodic table. Here's magnesium, and here's chlorine. So you should be able to find them first, and then you should be able to determine how many protons and electrons they have. So if I'm doing magnesium here, with its 12 protons and 12 electrons, you should be able to tell if it's a metal or a nonmetal. Magnesium is on the left side of the periodic table from the stair-stepping line, so it is a metal. It is a metal. And metals react by losing electrons. You should be able to find its electron configuration. So I'm going to take those 12 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 electrons, and figure out its electron configuration. The number of electrons that fill up the orbitals, that's what I put up here, the little numbers. The electron configuration, 1s2, 2s2, 2p6, 3s2. So 1s2, 2s2, 2p6, 3s2. That is its electron configuration. You should be able to identify the outer or valence electrons. You can tell by looking at the energy level. The biggest energy level number identifies the largest or outermost electron orbitals. That's the valence electron orbitals. There are 2 electrons. So if I wrote the dot diagram for this, magnesium would have 2 dots, one for each of those 2 electrons in its outer valence electron orbitals. If it's going to lose electrons, it's going to lose both of those electrons. So if it loses electrons, it's going to lose 2 electrons. And if it had 12 protons to start with and 12 electrons, if it loses 2 of those 12 electrons, now it has only 10 electrons. And if I find the difference between those 12 positives and 10 negatives, that's a difference of 2 positives. So magnesium has a 2 plus charge. It has 2 valence electrons, and that's for magnesium. How about chlorine? Let's do the same thing for chlorine. Chlorine, if I look for that one on the periodic table, again right there, it's a nonmetal because it's on the right side of the stair-stepping line. Chlorine has 17 protons and 17 electrons. It's a non-metal. It reacts by gaining electrons. It gains electrons. If I write its electron configuration, I'll take those 17 electrons, put 2 of them in each orbital. That's 10, 11, 12, 13, 14, 15, 16, 17 electrons. So I put 2, 6, 2, 5. So those are the electron configurations for chlorine. I'll write that out: 1s2, 2s2, 2p6, 3s2, 3p5. Now let's find its valence electron orbitals. Look for the energy level number that's the biggest, that identifies the largest electron orbitals. There are 7 electrons there. If I drew the dot diagram for chlorine, I would have 7 electrons. It needs 1 more in order to make 8, like a noble gas. So if it gains electrons, it gains one extra electron because it just needs one more. And so if it had 17 protons and it had 17 electrons and gained one more, it now has 18 electrons. The difference between those charges, one extra negative charge, chlorine with a 1 minus charge. So why do elements react? Elements are reacting because they want to have the same outer electron configuration as a noble gas. The noble gas elements, the ones that are in group 18, these are all very non-reactive. They all have completely filled outer s and p electron orbitals. Helium has 2 s electrons in its outermost only electron orbital, and the other ones all have s2p6. They have 8 outer electrons. They are completely filled outer orbitals, very stable and non-reactive. These elements do not react with the other ones on the periodic table except under extraordinary and often laboratory situations. But for the most part, we consider these to be inert. They don't react with the other elements. All the other elements are trying to react by exchanging electrons with other elements to get 8 outer electrons. Magnesium does it by losing its 2 valence electrons, and then the outermost orbitals in the second energy level will have 8 outer electrons. So when we draw magnesium reacting, we show that it's losing these 2 outer electrons to become more stable. Chlorine gains 1 extra electron, so that if it has filled its outer s and p orbitals, now it has 8 electrons like a noble gas. So that's why we show chlorine gaining 1 extra electron to become stable. Let's look at the positions of those 2 elements, magnesium and chlorine, on the periodic table. Magnesium is a metal and loses electrons. Chlorine is a nonmetal and gains electrons in chemical reactions. The reason why magnesium loses electrons is because it doesn't have as strong an attraction for its valence or outer electrons as chlorine does. Chlorine has a much stronger attraction for its outer or valence electrons. Why? What makes the difference between those 2 elements? So if you look at those electron configurations again, and if you look at the number of positive charges, the protons in the nucleus, it's these positive charges that are attracting the negative charges in the valence electron orbitals. These 2 electrons here, or these 7 electrons here. So how strongly does the nucleus attract those electrons? Well, one thing that you'll notice is that these electrons and these electrons are all in the same energy level. They're all in the 3rd energy level. And so you can think about that like they're the same distance from the nucleus. That the nucleus is having to attract electrons that are in the same energy level. Now these 12 positive charges are trying to attract these 2 negative charges. So they have to reach out to the 3rd energy level to attract those electrons. 17 protons, that's a bigger positive charge, are attracting electrons that are in the same 3rd energy level as magnesium. But because there's more positive charges, it's a stronger attraction. So that means chlorine holds on to or attracts electrons much more strongly than magnesium does. Both elements have to get through these inner electrons in order to attract their outer electrons. They have the same number of inner electrons, so that's not different between the 2 elements. The difference is how big are the positive charges. Another factor that might play a role is when you look at elements that are in the same group. Magnesium and chlorine are in the same period. Going across the period, elements all have the same size outer valence electron orbitals. It's always the same as the number of the period. This is period 1, 2, 3, 4, 5, 6, 7. The number that's in front, the 3rd energy level, elements that are in the 3rd period, 1, 2, 3, end with the 3rd energy level valence electron orbitals, 4th energy level for period 4, and so on. So elements in the same period, their valence electrons are in the same outer energy level. What's different when you go across the period is that the number of protons gets bigger. So there's a stronger positive charge attracting electrons in the same energy level. Going down the periodic table in a group, we have increasing size of the outer valence electron orbitals, and we also have more protons. But the size of the electron orbital tends to override the size of the protons in the case particularly of metals. So if we look at when we go down the periodic table in metals, they become more reactive because they are not able to attract their electrons, their valence electrons, as well as elements further up the table. Magnesium is a more reactive, less reactive metal than calcium or strontium or barium because it holds on to its electrons more strongly. Going down the table, less attraction for electrons. Metals react by losing electrons, so the better you are at losing electrons, the more reactive you are as a metal. The opposite trend on this side over here. Chlorine attracts electrons more than magnesium, but less than the other but more than the other elements going down the table. So iodine, for example, being lower on the periodic table with its electrons farther from its nucleus, attracts the electrons less. The stronger you're able to attract electrons, the more reactive you are as a non-metal, because non-metals react by gaining electrons. So as you go up the table, non-metals become more reactive because they're better at attracting electrons to their nucleus. Somewhere in your review packet there is a table of electronegativities. This is another way that we can compare the attractiveness of elements for electrons. If you look at what we were just discussing, the elements over here, the metals, magnesium, calcium, strontium, barium, you'll see that there's a number with them that's getting smaller as you go down the periodic table. That's the electronegativity number. It describes how strongly elements attract electrons. When elements are paired and are attracting the same electrons in a bond, which one of those two elements is more attractive to the electrons? Going down the table, the elements become less attractive for electrons because their valence electrons are farther from the nucleus. Going across the periodic table, the electronegativity increases because elements are attracting electrons that are in the same valence electron orbital energy level, but they're attracting with a larger and larger nucleus. As you go up the table on the non-metal side, elements become more attractive for electrons as reflected in their higher electronegativity value. That means they become more reactive as nonmetals because they're more attractive to electrons, and nonmetals react by gaining electrons. As you go down the table on the metal side, elements become more reactive because metals react by losing electrons, and they are less attractive to electrons going down the table as reflected by the lower electronegativity values. If you were to take any two elements and attach them to the wires of a galvanometer, you can tell which one has the stronger attraction for electrons because the needle points to the one that has the higher electronegativity and away from the one that has the lower electronegativity. We'll return to that idea when we look at chemical bonding. There are two different types of chemical bonds that we investigated. One is called an ionic bond, and the other is a covalent bond. Ionic bonds characterize electrolytes, which are materials that when melted into a liquid or dissolved in water, cause that to be a good conductor of electricity. Suppose I were doing an experiment where I put these materials into some water and tested the water to see if it were electrically conductive. I could predict before doing the experiment which materials would be good electrolytes or contain ionic bonds by looking for the presence of metals. Anywhere I see a metal, I have the possibility of an ionic bond because metals are elements that lose electrons in chemical reactions and nonmetals react by gaining them. When we have substances like water or niacin or these all contain nonmetals, hydrogen is listed as an element in these compounds, but even though it's on the metal side of the periodic table, it is not considered a metal here. Since nonmetals react by gaining electrons, these elements are all going to try to gain electrons from each other. They're going to combine by overlapping electron orbitals in a covalent bond. So if I were looking at calcium chloride, for example, calcium, a metal with 2 valence electrons, and chlorine, a nonmetal with 7 valence electrons. If I had 2 chlorine atoms, each of those would gain 1 electron from calcium to become oppositely charged ions. The calcium loses electrons, the chlorines gain electrons, and in so doing, chlorine gets 8 outer electrons like a noble gas, as does calcium. Something like water, though, the hydrogen has 1 outer electron, and here I've got 2 hydrogens here, each with 1 outer electron. Oxygen, a nonmetal, has 6 outer electrons, and if we could get the hydrogen here to share its electron with oxygen, or share its electron with oxygen here, so that they overlapped their electron orbitals, then they would have completely filled outer electron orbitals like noble gases. I'm going to draw a circle around the 8 electrons that oxygen gets and that hydrogen gets, and by overlapping their electron orbitals, that forms a covalent bond. Sharing electrons, covalent bond. Exchanging electrons here, ionic bond. The ionic bond forms oppositely charged ions. Calcium with its 2+ charge, and the chlorines with their 1- charge. Each one of them has a 1- charge. When you put this substance into water, these ions can float around and conduct electric current through the mixture. But here the electrons in water are stuck in the bond, so they're not able to conduct electric current. That's why water does not conduct an electric current, why all of these molecules do not conduct electric current. So the light would be off for anything that doesn't have any metals in it. But anything that does have metals in it would have an ionic bond, and we would expect the light to go on when tested. You can predict if a compound has ionic bonds by looking for the presence of metals, because the metals in the compound would lose electrons to become positively charged ions. The nonmetals would gain electrons to become negatively charged ions. If you see that the substances have no metals, then you can predict that they will overlap their electron orbitals and share electrons in covalent bonds and then be non-conductive. One of the things you should be able to do with ionic compounds is write the formulas for the compounds given their names using a table of ions. The table shows the formulas for the ions and their common charges. So for example, if I were given these positive ions and these negative ions to find compounds for their formulas, I would start by listing those ions. Fluoride with this 1- charge, hydroxide with a 1- charge, phosphate with a 3- charge. I'm finding those by looking at my table of ions. Lithium with a 1+ charge, manganese. If you see a Roman numeral, that tells you what the charge is, if there's more than one charge possible for that element. Cobalt with a 3+ charge. I showed you a little trick to use. What we want to do is get the same number of charges, positive and negative, so that the formula's charges add up to 0. So if I list lithium and fluorine, and I see that their charges are opposite and equal, then that means I just need one of each ion to make the formula for the charge. Make the formula for the compound. The charges add up to 0. If I did that with lithium and hydroxide, those charges add up to 0, so I just write one of each ion into the formula for the compound. However, if they do not add up to 0 right away, these two do not add up to 0. So what I'm going to do is I'm going to crisscross those charges to make subscripts. This will be lithium, and the 3 is going to come down and be the subscript, and then PO4, phosphate. I don't write a 1 down here. If I want to show there's 1 of something, I just write its formula, and there it is, 1 of them. So that would be the formula for lithium phosphate. If I were doing magnesium chloride, magnesium has a 2+ charge. Fluoride and magnesium do not add up to 0 with their charges. So I'm going to crisscross their charges to make subscripts. Magnesium will have 1 for the subscript, but we don't write 1 to show there's 1 magnesium, we just write magnesium. And then fluoride will have 2 for its subscript, so now these charges add up to 0. If I did magnesium hydroxide, hydroxide has 1 minus charge, doesn't add up to 0, so I'm going to crisscross the charges. But this time, since the hydroxide is a polyatomic ion, one that has more than one element, I'm going to have to add an extra step. So the magnesium will have a subscript of 1, hydroxide will have a subscript of 2, we'll bring that 2 down, but in order to put a 2 subscript on this whole thing, I'm going to put it in parentheses to show that it's 2 hydroxides. The whole thing is 1 ion, so I have to show that there's 2 of the whole ion to make this formula work. Magnesium phosphate, the charges don't add up to 0, so I'm going to crisscross them, and the magnesium will have a subscript of 3. I'm bringing this 3 down to make it the subscript, and the phosphate, PO4, will have a subscript of 2. I'll bring the 2 down, but to make this subscript attached to this ion, I have to put it in parentheses. Cobalt and fluoride, the charges don't add up to 0, so I'm going to crisscross the charges. It's going to be cobalt fluoride, like that. Cobalt hydroxide, the charges don't add up to 0, so I'll crisscross the charges, and cobalt with the subscript of 1, hydroxide a subscript of 3, but to make that subscript attached to hydroxide I have to put it in parentheses, that 3 right there. And last, cobalt 3 positive, phosphate 3 negative, those add up to 0, so I don't have to change anything. I'll just rewrite 1 of each, and that's the formula for that one. So in review, elements differ in how attractive they are for their valence electrons. Elements that are on the right side and on the top of the periodic table have the strongest attraction for electrons and more reactive as nonmetals. Elements that are down here on the bottom of the left side of the table have lower electronegativities, lose electrons more easily, and are more reactive as metals. Now sometimes in a chemical bond where electrons are shared in a covalent bond, the elements don't share the electrons evenly. So looking at the electronegativity table, you can predict which side of the bond is going to have more of a positive or negative charge. If you look at the electronegativities of carbon, 2.50, and hydrogen, 2.20, carbon 2.50, oxygen 3.50, oxygen 3.50, hydrogen 2.20, carbon 2.50, carbon 2.50. I'm just looking at the table of electronegativities and writing these in, 2.74, and then I can compare between those two elements which one attracts the electrons more. Just like we did with our lemon lab, looking at elements that we attached to the wires. The metals, the elements that we used were metals. They could conduct electric current, so we could see which way the needle moved. But in a covalent bond where there's no electrical conductivity, we don't see the needle move. But what we do have happen is the electrons are pulled towards one side of the bond or the other more. So between carbon and hydrogen, the electrons are pulled more to the carbon side of the bond. Stronger electronegativity, higher attraction for electrons. Between carbon and oxygen, oxygen pulls the electrons more towards its side of the bond. Between oxygen and hydrogen, oxygen wins the electrons more. Carbon and carbon, well, they're the same element, and when they're pulling on the electrons in the bond, those electrons that they share are shared evenly, so there's no one side or the other that's different. Between carbon and bromine, more on the bromine side, those electrons are pulled. The side that the electrons are pulled to has a slightly higher negative charge compared to the other side, a more positive charge. That results in polar covalent bonds. These polar covalent bonds act like little magnets in a molecule. And the way that those little magnets, those little polar covalent bonds, are arranged in the three-dimensional shape of a molecule gives that molecule polarity. To evaluate the polarity of a molecule, we look for its symmetry and we look for its dipole. So for example, ethanol here. Ethanol has symmetry down the middle from left to right. The two sides are mirror images of each other. But if you look at these elements and their polar covalent bonds, hydrogen loses electrons towards the carbon side of the bond. Carbon loses electrons towards the oxygen side of the bond. If you also look at these unbonded pairs of electrons on oxygen, those negative charges contribute to a very strong negative charge in this region of the molecule. There's more of a positive charge where these hydrogens are located. So if you divide the molecule down the middle this way, there is a definite difference in the charge distribution in the molecule, so that there's more negative on one side, more positive on the other side. We call that a dipole. When you can find that kind of non-symmetry in a molecule, that describes polarity in the molecule. However, ethane, for example, you can divide it down the middle this way or the middle this way, and it's mirror images all around. No one side is different from the other. That would be an example of a non-polar molecule. There's no polarity or charge-sidedness in the molecule, no dipole. Something else that we look for is whether or not hydrogen bonding is possible. Hydrogen bonding is indicated by the elements hydrogen, fluorine, oxygen, and nitrogen. Hold the phone is the acronym that I use. If I see that there's oxygen in a molecule, then I know that it's possible that it can engage in hydrogen bonding. The very strong electronegativity of oxygen attracts electrons towards its side of the bond much stronger than any other element that you might find in these compounds. Fluorine, oxygen, and nitrogen have the three strongest attractions for electrons. And will have a very strong negative charge in the molecule, giving the hydrogens that are attached to them very strong positive charges that can then attract to other molecules that have that same structural feature, either fluorine, oxygen, or nitrogen, and bonded to hydrogen. For more review on these aspects, please consult some of my other video demonstrations. We can evaluate the polarity of molecules by looking at how they mix or not. Things that are alike in their polarity or similar enough can mix. We use the rules of thumb: like dissolves like, or molecules stick to their own kind. Here's an example of an experiment that we did with chromatography, separating molecules by how well they mix with something that moves through a piece of paper. Back before I had a smartboard, I used to use those overhead transparencies, and I'd lick my fingers or use water on pieces of paper towel to clean off the ink. Well, on one of the Kleenexes that I threw on the floor, somebody noticed that the colors of ink were separating as the liquid, in this case my saliva, was moving away from where the ink started. The colors separated. The colors that were more like the liquid that was moving went farther, and the substances that were less like the liquid that was moving, this is water and this is polar, then the red dye is less like water and less polar compared to the green dye, because that one was more like water and moved further, mixed better, and was picked up and carried farther. The most recent experiment that we did on chromatography, that's the one that you want to look back on to see how we got those results. So this is by no means a complete discussion of all of the topics that are in the review. It is a review, not a reteach, but I do want you to have a chance to go through and look at those problems, and in particular to look back at your assessment problems that bear on the topics that are covered in the review packet. And if you have extra questions, please make sure to come and see me in homeroom, or I'll stay after school for a short time as well.